what is up, you guys? Welcome to the 13th lecture of this course entitled Machine Learning with TensorFlow and Scikit-learn. So in this one, we're going to introduce you to a very powerful machine learning model that is the SVM, or the support vector machine, along with its different linear variants. That is, we're going to introduce what a hard margin SVM is and its corresponding convex optimization formulation. We're going to see how to solve it using KKT conditions and the Lagrangian. We're also going to show you the soft margin SVM along with its convex optimization formulation, and using the same approach we're going to solve this problem. A Python implementation of both soft and hard margin SVMs is going to be given along the way for presentation purposes, and in the next lecture we'll be dealing with the nonlinear type SVM. So without further ado, let's get started. One of the most powerful and easy to understand models in machine learning is the SVM, or the support vector machine. Not only is it capable of performing linear and nonlinear classification, but it is also capable of regression and even outlier detection. It is probably one of the most popular models in machine learning, and it's really very interesting and mathematically a nice topic on its own. So in this lecture, we'll be modeling support vector machines. We'll show how to formulate a convex optimization problem that will lead us to different types of support vector machines, such as the soft margin, the hard margin, and even the nonlinear. So soft and hard are both linear SVM classifiers. We'll be also tapping upon nonlinear SVMs, such as the ones that utilize kernel methods, and we'll be seeing why we can, use kernels to generalize the notion of linear SVMs to nonlinear ones, thanks to a very important theorem, that is Mercer's theorem. So we'll be starting off by a given data set, the one that we see over here. So let's say I've got two features that are x1 and x2, and my interest here is to perform classification, right? So I'm given this data set. The circles are classified as maybe 0 and the squares as 1. So the fundamental idea behind SVMs is to fit a line, or in higher dimension a plane or hyperplanes, that separate or properly separate those two data sets. So many questions naturally arise here. So the first, that is my data set linearly separable? Is there any outliers in my data set? All those affect the performance of finding the optimal plane that separates both data sets. Okay? So naively speaking, what someone could do is, tweak around to find a really good line, right? To separate both data sets. So one might choose the following line, which is probably a good choice. The following red line, and say, oh, okay, I found this line that is a heuristic line, right? Because there's no mathematical explanation why we chose it, right? But as you can see, this line is supporting the support vectors. Let's put it that way. So what are support vectors in that case? There are instances. I'm going to highlight them over here. So this instance right here is a support vector, as well as this one. So those are both support vectors belonging to different data sets. And why is that? It's because if we center a hyperplane that, you know, falls in the middle between both data sets, well, those two vectors are on the edge of the street, right? So if I were to, you know, remove this line and say I'll insert this one over here and another one over here, right? It's as if those two vectors are points where those two lines pass to separate both data sets. So all I need is those 2 points to separate those two data sets. Okay? So in that case, what SVM or the hard SVM would do is pass a line in the middle of those two support vectors. Okay? And this hyperplane or line would then be called the support or the supporting hyperplane. Okay? So now the question is the following. How could I find this supporting hyperplane given my training set? That is, both data sets and their corresponding classes. Well, I did explain this in one of my convex optimization application lectures, which I'll be leaving down in the description section below. And I'll repeat the derivation over here because I want to also extend it to nonlinear SVMs. In the convex optimization application lecture, we were only restricted to linear and hard margin SVMs, okay? So over here, what we're given instances, right, of the form xk and their, which are vectors containing points x1 and x2 in this particular case, and their target values or their corresponding classes yk. So if xk belongs to the circle class, my yk is 0, else it is 1, right? Our aim is to find a hyperplane, right, that is of the form y equal w transpose x plus b, right? Our aim is to find w and b, so that for each x, I want to evaluate its corresponding class y. If it lines on top of the line, we say that we are in the square class, else we are in the circle class, right? So in other words, if we say that my y hat is 0 if w transpose x plus b is negative, or instead of 0 we can assign a -1 and a +1 if point x lies on top of the hyperplane w transpose x plus b, right? So as you can see over here, our aim is to find w and b with the following constraint, right? So those two equations could be seen as constraints. Now, replacing both constraints using one single equation, we can see that if I denote by, so let's say I'm given n samples, or n, the number of instances is n, so the number of squares plus the number of circles is n, then, and also referring to the kth instance as xk, yk, then the first equation satisfies yk multiplied by w transpose xk plus b, since this guy is negative and so is this guy, then this guy multiplied by this guy is positive. This is for the first case. But this is also true for the second case because yk is positive and so is w transpose x plus b. So this guy is a constraint, right? And actually it is the only constraint if we were to solve a hard margin linear SVM problem, okay? So what are we doing here? We are optimizing a certain cost function subject to this particular constraint. So I'm trying to minimize a certain cost, and we'll see what it is just about a bit. So this optimization is going on with respect to w and b because those are the two quantities that define the hyperplane. W is the gradient, right? And b is an offset. If b is 0, then this line would be passing through the origin, right? So we're minimizing a certain cost, and I'll state what it is just about now, and why, subject to this constraint over here. And this guy applies for k going from 1 down till n. So for all my training instances. Now what am I trying to minimize here? Of course I'm minimizing functions of w and slash or b, right? Okay, so what is an appropriate decision or cost function that seems suitable over here? Well, let's take a look at the gradient for a bit. We said that the gradient w is the one that defines, it's the vector that defines the direction of the plane, right? Then it seems natural to include w in our cost function. Now, let's say our optimal w, without loss of generality, is w1 and w2 in this particular case, right? Then again, bear in mind that w is a direction vector. Its magnitude doesn't hold any information, right? The magnitude of w is only going to, just amplify w, but it's not going to change, the sense of this line. That is, if my line looks like this, right? So if I come here and look at the objective function y hat, right? If I divide my w by an alpha, then my x's are going to be multiplied by an alpha. Look at it that way. So w transpose x is equal to 1 over alpha w transpose multiplied by alpha x. Now, the larger alpha is, you can see that my alpha x's increase. So let's say alpha is 2, then I divided my gradient or slope. I divided my gradient vector by alpha. Then my instances are multiplied by alpha. Let's say alpha is 2, then we get, instead of x, we get 2x. So my margin increases, right? Margin is this distance over here, right? This is the margin. Symmetrically, it's also this distance over here. So if I multiply my instances, x's by 2, then this point would be here, and this point would be here, and this point would be somewhere here. So we're increasing the margin. Thus, the constraint here is to minimize the magnitude of w. That is, we're interested in minimizing w transpose w, okay? And usually in references you find a half over here. That's because w transpose w is the Frobenius norm of W square, and thus when taking the gradient of this cost with respect to W, this 2 vanishes or cancels out this 2, right? And okay, so that's what we have to say about the cost function in case of the hard margin linear SVM. One last thing over here is that this problem is still loose. And why is that? It's because we're not taking this margin into account. Okay? Right here I'm saying, okay, so if you're giving me an xk along with its class, then I say it's 0. I say it's positive when my y hat is 1, and it's negative when my y hat is minus 1. Well, we're not leaving any margin. That's the thing over here. We're not leaving any margin. A proper way of doing that is saying that without loss of generality, that this line over here, or this support vector over here, is the one where y hat is minus 1. And this guy over here is y hat is plus 1. If we were to leave the problem as is, there's no margin because it's 0. So a proper way of taking this into account is by modifying those zeros into the margin values, that is minus 1 and plus 1 respectively. So I'm not going to classify only when W transpose X plus B is negative. No, this is even stronger when it's less than minus 1. So when it's below the support vector and not the supporting hyperplane. Okay. Likewise, I'm going to say that my X belongs to class plus 1 when W transpose X plus B is not only greater than 0 but greater than plus 1. That is the upper supporting hyperplane. Okay? So in that case, multiplying y hat by W transpose X plus B is not only positive but greater than 1, right? It's greater than 1 in both cases. So this is the problem I have to optimize. And since this problem is convex, why is it convex? So if you were following my convex optimization lectures, you can easily recognize that this optimization problem is a quadratic program. Why? Because the cost is quadratic in W and the constraints are linear in W and B. And thus, this is a QP, quadratic program. Okay? And so we can solve it easily using the Lagrangian function. So this is the problem we have, and note that this is a hard margin problem. Why is it hard? Is that because I'm classifying without accepting any outliers. We're going to see just in a few moments from now that there is also another modified version or softer version of this problem that accepts outliers. I'll explain it just in a few moments from now, okay? Now let's focus here and try to see how to derive W and B, okay? I'm also going to leave down in the description a link for my convex optimization lecture on quadratic programs. I really urge you to watch this lecture before the following derivations, okay? So before proceeding, I'm going to write down the Lagrangian function of this problem. That is a function of the variables and the Lagrangian vector lambda. So W is also vector, and lambda over here is a vector containing all the Lagrangian multipliers associated with the constraints, lambda 1 down to lambda n, right? So the Lagrangian function, if you're following my convex optimization lectures, is nothing other than the cost function, half W transpose W. And since we're minimizing, we're going to have a minus lambda k multiplied by the kth constraint when positive. That is, I'm going to get the 1 on the left hand side. It's a minus 1, so I'm going to multiply lambda k with the kth constraint when 1 is on the left hand side, so the constraint is positive, and hence I'm going to get yk into w transpose xk plus b minus 1, right? And don't forget that we're going to sum over all such weighted terms. Okay? Now, what you probably know from high school is that using basic calculus, once you have a Lagrangian of the problem, then it suffices to take the partial derivatives of the Lagrangian with respect to the unknowns, w, b, and lambda, set them to 0. You get a system of equations in w, b, and lambdas, and you solve for those unknowns, right? However, this method only applies to equality constraints. That is, when I have a problem with equality constraints. But fortunately, under some regularity conditions, which we have over here, we can also follow the same approach even when we have inequality constraints. And these regularity conditions are the so-called KKT conditions, that is the Karush-Kuhn-Tucker conditions. And what are they? That is, if you solve the problem as if we have an equality constraints, given that the solution, let's denote it as W hat, B hat, and lambda hat, satisfy the KKT conditions. I also have a lecture on KKT conditions that I'll be leaving down in the description section. So one, we have to, the solution achieved by equality should respect the problem's constraint. That is, all yks multiplied by w hat transpose, that is the solution, xk plus b hat should be greater than 1. That's 1. And 2, all my lambda k hats should be positive. And 3, we should have complementary slackness. And what is complementary slackness? It means that either lambda k is 0, or that is for the kth constraint, either lambda k is 0 or the green term is 0. What does it mean that the green constraint is 0? It means that my kth instance lies on the boundary. What happens when this term is achieved with equality? It means that xk lies on one of the margins, right? Either this line or this line, depending on the value of yk. Okay, so KKT conditions give us necessary ones for a stationary solution or point to be a solution for the constrained optimization problem. So after obtaining the solution, if you verify that all 3 solutions are achieved, that means your point is the optimal point. And indeed, in the SVM, this is the case. So let's first proceed by computing the gradient with respect to w, so nabla w, of the Lagrangian function. I'm going to omit, for sake of compact presentation, that L depends on WB and lambda. So what happens when I take the gradient with respect to W? This term becomes, so when applying a vector derivative on W transpose W, we get a 2W. And this 2 will cancel out with this 2, leaving us with W. Okay? Now over here, this term is linear in terms of W, right? So what I'm going to be left with is only this term without the W. So as if you're deriving 2x. What's the derivative of 2x with respect to x? It's 2. So what are the terms that are independent of W in this part over here? It's lambda k, yk, xk. Note that lambdas and y's are scalars and the x is a vector. Okay? Now let's apply the partial derivative with respect to the scalar quantity b. What do we get? We can see that the only term depending on b is the sum on lambda k, yk. And don't forget the minus over here, so we get minus sum lambda k, yk. Right? So if I set both terms to 0 to obtain the stationary points, or point, we get that from the first order condition, the first equation, we get that my solution of W takes the form of this guy over here. So I have both conditions, W hat, that is this guy. I know my x's and y's, they're the given training set, right? But I don't know the lambdas. Likewise over here, I get this condition over here, that is the scaling, the linear combination between lambda and y has to be 0. That is lambda vector and my y vector. If I stack all my instances, y1 down to yn in one vector, call it y, those two vectors should be orthogonal. That is lambda transpose y is 0, right? Now I have a closed form solution of W, but I don't have one for B. That's another problem. So we have two problems right now. What is my lambda? And what is a closed form solution of B? Okay. Well, for B, don't forget that we have our good old friend, or friends, Karush and Khan and Tucker. They tell us that, okay, your solution has to respect all three. Lambda k positive, no problem. I'll show you why this is no problem, as well as the complementary slackness. We'll see this just in a few moments from now, but take a look at condition 1. Condition 1, they tell us, okay, your solution is optimal as long as 1, 2, and 3 are satisfied. Now, let's tighten 1 up. Let's say that, okay, I'm going to solve my problem, but I'm going to solve it with equality. That is, yk into w hat transpose xk plus b hat, which is what I'm looking for, is 1. What have I done here? I have tightened my inequality. It still satisfies the KKT because the KKT tells me that it shouldn't be less than 1. It should be greater than or equal. I'm going to take the extreme case, which is equal, just to find a closed form solution of b hat. How's this helpful? Well, just express this equation in terms of b hat as isolate b hat on one side. You're going to get that yk b hat is equal to 1 minus yk w hat transpose xk, right? And there you go. So once you computed w hat, let's say you have computed w hat, you know your xk's and yk's, so you can compute b hat. How? Well, to make use of all the training set, notice that this applies from k going from 1 till n. You can average both left and right hand sides. That is taking the sum over yk's going from 1 till n. So over here, you can go from k equal 1 till n, yk, right? So one last thing over here is to notice that yk is either plus 1 or minus 1, right? Now to get rid of this yk over here, I'm not going to divide by, well, you could divide by yk, but if we multiply by yk on both sides, look what we get. So we get a yk square b hat is equal to yk minus yk square w hat xk, right? Same thing, k going from 1 down to n. Notice that yk square is nothing other than 1 because yk is either plus 1 or minus 1. So I get b hat, that is yk minus, I forgot a transpose here, w hat transpose xk. And this thing also applies for all k, going from 1 down to n. Now, this gives you an estimate using only one training instance, xk, yk. However, we can use this for all my training instances, right? So it's preferred to take an average over all such terms to robustify the quality of estimation of b hat. So for that, we're going to average over all such terms, but that's where the second KKT condition comes into play. We're not going to take all of them from 1 to n. No, we're going to take the ones that give us a positive lambda k. Okay? So if we denote by, I don't know, what do you want to call it? Let's call it n subscript lambda. That is the number of elements or training instances that correspond to a positive Lagrangian multiplier. We're going to average over all those terms. So n lambda, let's call n lambda the set. So this is the cardinality. So let me write down n lambda. N lambda is the set of xk yk such that lambda k is strictly positive, right? So over here I'm summing over such training instances. Okay, good. Okay, so now I have a closed form solution for b hat. I have a closed form solution for w hat, but in order to compute w hat, I need the lambdas. And even more, in order to compute b hat, I need w hat. So given lambda, I compute w, and given w, I compute b. So without the lambdas, I can't do anything, right? So how do I get my lambdas? Well, if you've also been following my convex optimization lectures, you'd see that we spent a lot of time talking about the duality concept, and that for every primal optimization problem, there exists a dual problem. There exists another problem that is more or less very related to the initial problem that we had, the primal one. Okay, so what is the dual problem? Actually, the dual problem is the problem where instead of minimizing the cost, I maximize the Lagrangian function at w hat and b hat. So I'll be maximizing with respect to lambda. And actually this function has a name. It's called the dual function, the Lagrangian dual function. And in my lectures, I denote it as g of lambda. So g of lambda is actually the infimum, but in this particular case, it's the min on w and b of the Lagrangian function, L, w, b, and lambda. That is L, w hat, b hat, and lambda is the unknown right here. So let's find out this guy, which is g of lambda. So after I find out an expression of g of lambda, my objective would be to maximize over lambda the function g of lambda subject to the second KKT condition. Okay? Subject to positive lambdas. So this is actually referred to as the dual problem. And also under some conditions, the primal and dual have zero gap, duality gap, which in this case is also conserved. Okay, so let's find which is in this case satisfied. So let's write down an expression of g of lambda, right? So g of lambda is the Lagrangian at w hat and b hat. So it's this guy at w hat and b hat. So it's this function. Now let's expand this term over here. What we get is, okay, so my w hat transpose times w is over here. And let's expand this. We get three terms. That is, the first one is lambda k, yk, w hat transpose xk. The second one is lambda k, yk, b hat. And the third one is plus a sum on lambda k, right? Okay. Let's extract terms that do not depend on k outside those sums. So what we get is w hat transpose goes outside. So k going from 1 till n, lambda k, yk, xk, right? Minus b hat into sum on lambda k, yk plus a sum on lambda k, right? Now, what is this term over here? If we go up here, sum on lambda k, yk, xk is w hat. So sum on lambda k, yk, xk is w hat. So we have two terms, w hat transpose w hat. So we've got a half minus a 1. That's a minus half. W hat transpose w hat. And the third term, we have a sum on lambda k, yk. Well, we just saw in those first order conditions that the sum on lambda k, yk is actually 0. So this guy over here is a 0. And we're left with the sum on lambda k. Well, now, since my problem is to maximize g of lambda with respect to lambda, then I have to express my w hat again in terms of lambda. So I'm going to have two summations. Well, since I have two summations, it's better to express each one in terms of different indices because I'm going to multiply them with each other. So the first one runs on I. So lambda I xi yi, and the second one, same thing, but it's running on j, right? So lambda j xj yj. Then we've got a sum on lambda k. Okay, let's multiply both summations to get a minus half and a double sum on I and j. Lambda I, lambda j are scalars. Yi, yj are scalars. And an xi transpose. Ooh, I forgot a transpose over here. So xi transpose xj plus this sum over here on lambda k. This is my g of lambda expressed in summation form, subject to lambda positive, okay, entry wise. So we're not going to solve this problem over here in terms of lambda because it's an easy problem, I can assure you that. And the way you can see it is that this guy is actually a quadratic program. Is it convex? Well, we have to express it in matrix form so that we can discuss that further. So what I'm going to do here is that we could notice that since we're maximizing in terms of lambda, then I'm going to express the maximization term as follows. So we get a lambda transpose. Well, we have a minus half. So we're actually maximizing a minus half lambda since we have a double sum, the quadratic term over here. So it's a lambda transpose p lambda plus we have this linear sum over here, could be expressed as f transpose lambda. Let's start with the easier term, which is the linear part. So since this guy is a sum on lambda, the coefficients of the lambdas are all 1. So my f should be a vector loaded with all 1s, right? Okay, that's my f. What about my p? Well, my p is a matrix where its ijth entry is, let's see, lambda I, lambda j multiplied by this term. So it's this term over here. So it's a yi, yj, right? Multiplied by an xi transpose xj. Correct? Okay. Now let's zoom in on this matrix and let's verify. Is it symmetric? Well, what is pji? It is yj yi xj transpose xi. Well, yj yi is yi yj, no problem. And xj transpose xi is the same as xi transpose xj. So pij is pji, hence p is a symmetric matrix. Okay. And the second important question is that, is it positive semi-definite? Well, actually yes it is, because you can express P as a product of two matrices, non-zero matrices. And what are they? Well, it's U transpose U, where U looks like this. U is a m by n matrix that, you know, in its first column we've got a y1 x1, y1 scalar, x1 vector, down till the last column we've got a yn xn, right? So since this matrix is in the form U transpose U, then it is positive semi-definite. Why is that? Well, using the definition of positive semi-definite matrices, for every vector Z in R, you have to prove that Z transpose PZ is positive. Is that the case over here? Well, let's plug in, instead of P, a U transpose U. We get a Z transpose U Z, that is UZ transpose into UZ, right? That is the Frobenius norm on U of Z, which is always positive. So for any Z, this quantity Z transpose PZ is non-negative, and hence P is positive semi-definite. Hence this problem over here is a quadratic and convex optimization problem, which you can easily solve, right? This problem is easily solved. You can easily write down the Lagrangian function of this problem. You can solve it easily using the same recipes that we presented over here. And hence, after you solve, now, if you have problems solving this problem, you can kindly leave a comment down in the comment section below, and maybe you're stuck on a step, I can further assist you. Maybe you want me to conduct another lecture presenting how to solve the dual problem of the SVM. No problem, I can prepare such a lecture. And if not, well, you get your lambdas, and once you have your lambdas from this dual problem, you go back here, you stick them inside this equation over here, you have your W hat, that's done, you get your W hat, and after you have your W hat, you go back down here, you stick it inside this equation over here, and you get your B hat. And that's when you realize that you performed a hard margin SVM. Okay? So that's how you formulate a hard margin SVM problem, and that's how you solve it. And that's when you notice that sometimes it works, but sometimes it doesn't. And why is that? It's because sometimes, or most of the time, you have outliers in your data, and a hard margin SVM is really sensitive to these kind of problems. So let me show you what I mean. So instead of, let's say I've got one of those circle points right over here, right? So the first question is, well, is my data linearly separable? Well, if it weren't for this annoying point right here, then yes. But this point is really annoying. That's what we call in statistics an outlier. It's an annoying point. It's a point that, it's a misfit. It doesn't belong where it actually belongs. Okay? And that's where you have to start saying, should I take a hard decision over here, or should I loosen things up? And what we mean by loosening over here is, instead of placing this line over here to separate my data, what could I, just cheat a little bit and put it over here? Maybe just stick it over here. Well, that's a really smart approach, and that's when you can formulate another problem over here reflecting this softness. Okay. Now before we get into the soft margin linear SVM, it's worth spending some time to see how to get SVM up and running on your Jupyter notebook on Python. Okay, so for that, let's import the dedicated libraries or modules. So we need the SVM classifier, SVC, from sklearn. Also going to import some data sets. I'm going to be needing the NumPy. And for plotting, I'll use the matplotlib inline, and we'll import matplotlib as MPL. And from matplotlib, I'll be needing the pyplot. Okay. So this is a percentage, not a dollar sign. Okay. So now let's import the iris dataset that is achieved from load underscore iris as such. And my training dataset would be iris as such data. Let me see how this looks like. X. So we need the length and the width. So the first and second columns are length, petal length, and petal width respectively. So I can extract them as such. Right? Okay. And I will be extracting the target values, the y's. Okay. So this is my y's. Now, as you can see, I have 3 classes. I'm only going to be interested with binary classification. That is, I'll pick the y's that are either 0 or 1. And that could be achieved as follows. So 0 is setosa and 1 is versicolor. So y equals 0 or y equal to 1. I'll extract the x's that correspond to those indices and their associated target, as well as their associated target values. Oh, so this is not C++, so this is not C++, and I need one pipeline as such. Okay, now let's define an SVM classifier using the SVC. I'll specify a kernel that is linear, and we'll specify the C hyperparameter, which we'll be seeing in just a while from now when we talk about the soft margin. But for the hard margin, we set it to infinity. Okay, so let's fit y versus x, and there you go. We have our SVM ready in the SVM underscore classifier, or CLF. Okay, so now let's define an x0 or an x-axis. So let me see the range of my x's. So 1.4, 0.2, 4.5, no more than 5 and no less than 0, right? Is there a 5? Yep, there's a 5 here. So I'll go for 5.5 as max. So let me define an x-axis. That is x0. Going from 0 to 5.5, and I'll take 200 points. Now let's define a function that will plot my decision boundaries. Okay, I'll pass it the SVM classifier as well as xmin and xmax. Okay, so my W is actually stored in SVM underscore CLF.coefficient as such, and my B is the intercept. Now, at the decision, I'm going to have to plot the W transpose X plus B, okay? So since I'm dealing here with 2 features, right? So X is X1, X2, and W is W1, W2, then this guy could be written in this particular case as, so if I start my indices as such, let me go down here to make me some space. So if my y is w transpose x plus b, and my w is w0, w1, and my x is also x0, x1, and I can express this as w0, x0 plus w1, x1 plus b, and at the decision boundary, this guy is 0. So I'm going to express x1 as a function of x0. How can I do that? Well, that's easy. w1, x1 is minus w0, x0 minus b, right? And then I divide by w1, I get an x1 that is minus w0 over w1 x0 minus 1 over w1 b. So I need this equation over here. Right here. So that's what I need to, generate. So given my x-min and x-max, I'll generate another x0 going from x-min, x-max, take 200 points, and then I'll get my decision boundary, right? Which follows the following equation. So it is minus w0 over w1 times x0 minus b over w1, right? And, well, what is my margin over here? That's a good question. Well, it is when the same term is, instead of 0, it's evaluated as 1. So it's when w0, x0 plus w1, x1 plus b is 1, right? So expressing x1 as a function of everything else, we get that x1 is 1 over w1, right? Minus w0 over w1 x0 minus 1 over w1 b. So it's the same term plus a 1 over w1 in case we're on the upper margin, and it's a minus 1 over w1 when we're on the bottom margin. So let's take this margin, that is the additional term, 1 over w1, so 1 over w1, and define the upper and lower margins. So upper margin is the decision boundary plus the margin, and the lower margin is the decision boundary minus that margin, right? Now let's take the support vectors that are SVM underscore CLF dot support vectors, right? Let's plot a scatter plot containing the support vectors. First component versus the second component. And let's specify some fancy face colors. So let's enter the following hexadecimal color code. Now let's plot in the 3 boundary lines. The first one is the decision boundary. I'll plot it in black. The second one is the upper margin. I'll plot it in dashed black. And the last one is the lower margin that I will also plot in dashed black. We'll open a figure. And on that figure, I will call this function, right? Pass it my classifier and my xmin and xmax. So xmin is 0, xmax is 5.5. Let me see how the figure looks like. Oh, I'm still inside that. You should be careful when indenting as such. Okay, so that's what I'm plotting right now. I'm plotting the decision boundary, the lower and upper margins. Now let's plot the data set. So the ones for y equal 1, I'll plot in this color, and the ones for y equals 0, I will plot in another color. So in yellow circles and the first one in blue squares. Let's see how the plot looks like. Okay, not bad. And let's give an X label, call it petal length as such. And let's limit our axes to 0, xmin and xmax, ymin and ymax. And there you go. So as you can see, SVM grabs the support vectors, passes the margin boundaries, and then fits in the decision boundary so that any arriving point is tested whether it lies on top or on the bottom of this decision boundary. If it's on the top, it's a blue square. If it's on the bottom, it's a yellow circle. Okay? Okay, now let's see what happens when I add some outliers to my data. Let's say I've got 2 outliers. Say the first point is 3.4, 1.3, and the second one is 3.2, 0.8. And they're both classified as yellow circles that are class 0. Okay? Okay, so don't forget the double brackets in the first one because it's a matrix. Okay. Now, X01 is the data set containing the first outlier. So we're going to concatenate on top of my original data set this outlier. Along the 0 axis. And its corresponding Y01 is using the same thing. Copy paste it here. Y over here and Y over here. And X02 is the one containing the second outlier. As such. Okay? Now, let's create a classifier on the first dataset. Actually, let's see how the datasets look like. So, going to open a figure with the following figure size, and in the first subplot, call it 1 to 1. Second subplot, call it 1 to 2. Let me show the subplot. Okay. In the first subplot, I'm going to plot x01 where y01 is 1, x01 so that's the first class in blue squares, and likewise the second class in yellow circles. Okay, as you can see, here's my outlier. Let's stick in an arrow over here saying this is an outlier. Okay, so the way you can do this is using the annotate function of plot. Say this is an outlier. Okay, it's missing some arguments that are the xy that should be pointing on the first outlier as such. Okay, let's fix this by including a center. Okay, let's increase the font size, say 16. Okay, now let's indicate that it is a text with the following coordinates. Okay, now let's put in an arrow. Arrow props. It's a dictionary containing the color, which we will color as black. Okay, let's shrink it because it's too. Okay. I think the minimum is 0.1. Okay, that's good. Now let's limit our axis to, I don't know, plot axis. So x min, x max, y min, and y max. Looks good. Now I'll do the same thing for the second data set. So I'll copy paste just what I have over here. Instead of O1, I have an O2. Right? And over here it's a 1. It's the second outlier. Okay. Looks good. Now, all I have to do is run SVM here and here. So I have my, I still didn't, okay. So let's create an SVM classifier 1 on the, using SVC, linear kernel, pass it the C, that is infinity, means hard kernel, and fit y01 versus x01. Likewise, I'll create a classifier, call it 2 on the second dataset as such, right? Now, just over here, I will call the function that we wrote over here to plot the decision boundaries, right? So plot SVC score decision boundary. I'll pass it the classifier, which in this case it's CLF1, passing it x min and x max. And as you can see, it's taking a lot of time because of the floating point precision. So right here, instead of infinity, I threw in a large number and it's working. And as you can see, we don't have margins right here because SVM failed on this dataset. And the reason why is because this dataset is not linearly separable. As you can see, we don't have any, margin. Actually, the margin is 0. Let's try to, print the margin. So str margin, actually it's a print like this. Okay, there you go. The margin is really small as compared to the previous case. Okay, so really small. That is, the margin is actually on, the upper and lower margins are actually on the decision boundary. And the way we can see that is to zoom in over here. Can do this by limiting the x-axis, let's say between 2 and 3. As you can see, they're over there. Okay, let's limit, let's say, the y and x, the y values, I don't know, between 0.5 and 0.51. Oops. So let's say between 0.5 and 0.6. Nah, it's not working. It's over here. So there you go. Okay. Okay, let's return those values as they were. There you go. Okay. So the margin is 0. We couldn't find a proper margin to linearly separate both data sets. So that's where it fails. However, over in this case, actually, the arrow here is aligning on is covering my data set. So let me move that just a bit. Let me change this over here. Okay, better. And let's plot the decision boundaries over here. As you can see, a small margin, of course, due to the outlier, but we managed to separate both data sets. This outlier still falls here, but it's an outlier. It's not around them as normal as it should be. No, it's pushed away from its friends, right? Okay, so we have a problem. What is it? It's when I'm given a data set that is not linearly separable. I cannot run this type of SVM. That is a hard SVM. And that's where the smooth or soft SVM comes into play. So instead of this problem, instead of the hard margin SVM, which looks like this, we're going to take a smooth approach or a soft approach. So we're going to add new variables over here, which we will be calling xi, right? That will, make this problem softer. And what I mean by softer is that I'm allowed, so if we go back here, I'm allowed, or let's put it that way, and I'm going to let this outlier, for a moment, I'm going to cover my eyes and allow this outlier to fall with the blue curve, with the blue class, okay? So with that said, this will change the problem completely. That is, we're going to have a new line over here that pretends that this outlier falls with the blue within the blue class, okay? And we're going to carefully modify the problem so that we're allowed to do so. So we're going to have a softer constraint. So over here, instead of a 1, I'm going to have a 1 minus psi I, psi k. So I've got n xi's. Psi k is for the kth training set. So for each training instance. So for each instance, I attach a psi k with it, which is going to serve as a smoothing parameter that allows me to, move the margins to, fit the data better. Formally speaking, this new constraint will allow an adaptive margin. That is, so here my psi k's are positive, they're not allowed to be negative. If it's negative, it means I'm getting a smaller margin. So those xi's are allowing an adaptive margin, and the cost will thus penalize those xi's. So we're going to have a hyperparameter over here that operates a certain that reports a certain trade-off, and we're going to sum over all xi's as such. So if a certain data point is not an outlier, psi k should be, between 0 and 1, so that this term over here is positive. So in that case, I have a small penalty. I don't penalize this instance, okay? However, when a certain outlier is classified in the wrong class, this psi k is going to be greater than 1. And if that's the case, then my cost function is going to, it's going to increase. So that said, I'm going to try to minimize all misfits. So not only am I doing hard, so this term is the hard part, right? Is hard margin. So not only am I applying hard margin, no, I'm trying to minimize the effect of outliers, right? So if there is an outlier that, I can't do anything about, it's going to be penalized in the size, okay? And as you can see, we have a C parameter over here that is a hyperparameter. It will control the relative weighting between the cost of making the margin small and ensuring that most training instances have adaptive margins that are at least 1 in the ideal case. Therefore, we're going to minimize the total sum of penalties as well. Okay, does that make sense? So if I were to write down the Lagrangian, it is, oh, and by the way, the minimization is also with respect to psi. And this problem is now the soft margin, SVM. So the Lagrangian right here is a function of W, B, psi, and our lambdas, which is the cost half W transpose W plus C sum on psi i's minus sum on I going from 1 till n lambda I multiplied by this thing minus this thing. That is yi into W transpose xi plus b minus 1 plus xi. Now, as before, this problem is a quadratic program. The cost is quadratic in terms of w, linear in terms of xi, and we've got linear constraints. And they also satisfy the KKT conditions. So I'm allowed to, solve the partial derivatives with respect to L. So setting the gradient with respect to W on L, we get that over here, we get a W. And right here, we get a minus sum on I, lambda I, yi, and xi, right? Setting this thing equal to 0, we get the same expression on W. Now, let's derive with respect to B on L. We get the only term depending on B is the sum of lambda I, yi, B. So the derivative of that with respect to B is sum on, or minus sum on lambda I, yi. That is 0. So right here we have another condition that should be satisfied. And last but not least, we need the derivative on xi of L. But, which is, so over here we've got a C sum on xi. That is a C, okay. Then over here, the only term depending on xi is lambda I xi. That is minus lambda I, that's 0. So we get that lambda I is C. Actually, this guy over here is an upper bound on lambda I, because we're solving the problem with equality constraints. And all my lambda i's should be positive according to KKT, so this guy translates to all my lambda i's is positive and my C is the upper bound, right? Now we have an expression for W, we need an expression for B. And as we did in the hard margin case, the B could be achieved from the equality from the KKT condition, the first KKT condition, that is yk w hat xk plus b hat is equal to 1. So we satisfy the kth constraint with equality. In our case, it is yk into w transpose xk plus b is equal to 1 minus psi k. Multiply by yk on both sides and use the fact that yk square is 1 because yk is plus or minus 1. We get that w transpose xk plus b is yk into 1 minus psi k. Then b is yk 1 minus psi k minus w transpose b. Okay, and of course you can average to, as we did in the hard margin SVM, you can average over all instances to achieve a more robust estimator of b as such, minus w transpose b. Now, as previously, we need the lambdas to compute the w and the w to compute the b. So we need the dual over here. And the dual is achieved by replacing W hat and B hat in the cost. So as previously, we can see that if we replace W hat and B hat over here, so W hat, B hat, hats everywhere, W hat, B hat, we have that the sum on lambda I, yi times B hat, that has to be 0 because of this condition over here. So this term is gone, and this term is actually combined with this term to give me so going down here, it gives me a minus half W hat transpose W hat. Okay, and the C sum on lambda I on xi I, and right here you have a minus sum on lambda I xi I, where lambda I is C. We're solving with equality, so both cancel, and you're left with a plus sum on lambda I. So you get the same exact dual function as before to compute the lambda k's, which then you can compute the B hat and then the W hat. Okay? And that's how you solve soft margin using the Lagrangian function. Okay? Now let's see how to implement soft margin SVM on Python. So since I'm going to be training more than one SVM, it's better to use pipelines. So from sklearn.pipeline, I'm going to import a pipeline. So let's first so I have my iris up here, right here. I'll copy paste this code right here, but this time I'm going to take the iris that is 2 as one class and 1 and 0 as another class. And I'll use as type MP float. So I'll copy paste the code that I had previously. So this is the data set, and as you can see, we've got some outliers over here. They're overlapping. Let me limit my axes in both plots: xmin, xmax, ymin, and ymax. Okay, you've got here some outliers. Now let's see how two different soft margin SVMs perform. Okay, so to launch a pipeline, I'm going to first use the scaler, and for that I need to import from sklearn.preprocessing going to import the standard scaler. The scaler is a standard scaler. Oh, it's not pro-processing, it's pre-processing. Okay, we can do without this pipeline thing. Whatever, I'm using Python 8, and it seems that It's not working. Okay, so let's do each one separately. So linear SVC. I'll pass the C hyperparameter 1 first. I'll indicate a hinge loss and another one, but with a larger C, let's say 100. So to get your linear SVC, you go to sklearn.svm and import linear SVC. Okay, and now let's fit. So svm.clf1.fit y versus x, and same thing for 2. Okay, we have a warning, no problem. And right over here, I'll call the function that we implemented earlier on svm underscore clf1 xmin xmax, and we don't have support vector attributes, right? So we need to compute that. We need to do this manually. And there you go. So as you can see, with a smaller C, we accept more outliers, right? As C goes large, we have less and less outliers, right? So the C is a trade-off hyperparameter. The larger it is, less outliers, but also a smaller margin. The smaller C is, we have more outliers, but a larger margin. Okay? So that's about it. For this lecture, we pretty much did a lot of stuff. We started out by what an SVM is, how to formulate both hard and soft margin SVMs, how to formulate their corresponding convex optimization problems, and how to solve them using the Lagrangian and KKT conditions, along with their respective Python implementations. So thanks for watching. If you found this lecture beneficial, please leave a like on the video, subscribe to the channel. If you have any questions whatsoever, kindly leave a comment down in the comment section below, and I'll make sure I'll get to it as soon as possible. Also consider donating to my Patreon account any amount you wish. Thanks for watching, and I'll see you in future lectures.